So he has been helping me, and I just saw Dao Huang, is that how it's pronounced? And they have been wonderful people. So without further ado, let Phil take over the talk. Thank you, Phil.
Okay. Well, according to my records, my first attendance of ATCM was actually in 2006 in Hong Kong. And I didn't have a camera with me, which was really unfortunate because I actually double-decker bus with an advert of a Casio ClassPad going past. I'd never seen an advert for a graphing calculator that big on the side of a bus. But all I've got is a stock picture here. What I was talking about in Hong Kong was geometry expressions, and we view that as a geometry add-on to a computer algebra system, providing the ability to talk geometry and algebra at the same time and communicate the algebra to a fully fledged computer algebra system to do fully fledged computer algebra on. What I'm going to talk about today is a development from geometry expressions, relatively new, GXWeb, which is a free browser-based version of geometry expressions. But we have the same philosophy of working hand in glove with a computer algebra system, and I'll be showing us working with another free browser-based piece of software, WolframAlpha. But I don't want to just sort of talk in generalities. I want to anchor my presentation in a specific problem. So what I'm going to look at is the caustic curve for a parabola. Now, if I look in my book, Catalogue of Special Plane Curves by Dennis Lawrence, he tells me that for light coming perpendicular to the axis of a parabola, the caustic is Chernhausen's cubic. And so that's what I want to look at. What is the caustic curve? Well, here's light emanating in a fixed point. When it hits a parabola, it reflects, and we get a curve emerges. This is the caustic curve. Here's just the reflected rays here. What it is mathematically is the envelope of that family of lines. That is the curve which is tangential to each member of the family. There's the curve in red, and we can remove all our lines and we get the caustic curve there. Another way of looking at the curve is to look at two kind of neighboring rays and intersecting the reflections. So there's the intersection between these two neighbors. It looks like it's fairly close to the caustic curve, and of course you can take it to the limit, and in the limit it will in fact lie on the caustic curve. So that's a second way of thinking about the caustic as a limit of a locus as opposed to an envelope. So with that, I'd like to go live with GXWeb, and we can take a look at the software. So here's GXWeb. You can find it at geometryexpressions.com. Let me just give you a little walk through the user interface, as it might not be familiar to you. It's slightly different to geometry expressions. There's some fairly straightforward stuff here, but the three main buttons are here. This one lets you create geometry, fairly obvious: point line, circle, infinite line, vector, and curve or function. Notice there's no conics. The conics are in geometry expressions, but not here. So I'm going to have to fudge to get my parabola. The second one are constraints. Now, because geometry expressions is constraint-based, the constraints are an important part of the user interface. And none of them are highlighted at the moment. None of them are enabled at the moment. That doesn't mean we have to pay more money. What it means is that we need something selected before they become enabled. Now, we have a little question mark that is enabled. If you want to know what you need to do for this constraint, distance length, select 2 points, 2 lines, 1 point, 1 line. Tells you what you need to do. And if you need more, it'll give you a little bit of a video to see how. The third one here is constructions. Again, none of them are enabled without anything selected. And this one's one we're going to use a lot. That's locus envelope construction. So without further ado, I need to make a parabola to start reflecting light in. So I'm going to use a function because I don't have conics. What I want to do is start off with the parabola y equals x squared. Now, the function, geometry expressions, the philosophy is that you sketch things first and then you specify once you've sketched. So using constraints typically on the geometry. But the function command in geometry expressions doesn't work that way. You just actually type in the function that you want, perhaps with some parameters. So we felt with GXWeb, we really wanted to go more in the direction of sketch first and then specify. So that's what we do with the function. So here's a function. We get the yellow notepad to say you've got to do something to get it white again. So if I sketch a function, geometry expressions will take a guess as to what I meant. So it's guessing here that I meant a sign, and it's put in some parameters and fit them to what I sketched. Of course, that's not what I wanted. I want x squared. You can always override what it gives you. So there's my function y equals x squared. Now, I would like the focus of this parabola for reference. Now I could create it by projecting light, reflecting it, and intersecting it with the axis, or I could apply previous knowledge. I happen to know that the focus of y equals x squared is 0 1/4. So I've put my point at where it's going to be the focus, and set that in there. Now, in the course of the talk here, I'm going to be doing a lot of work to keep my drawing, my model as clean as possible. So I'll start off. I select these two pieces of information which are useful, but I don't want to see them all the time, so I can hide them. So a long press is what brings up the pop-up menu with GXWeb. So what I'd like to do is look at the reflections of light that is coming in horizontally, perpendicular to the axis of symmetry, because that's what my book tells me is the Chernhouse cubic. Not from a finite source, like as I was showing on the slides, but from a point at infinity. So parallel rays coming in horizontally. So to do that, I'm going to need to create a tangent that I can reflect in. The software will let me reflect in a line. So once I've selected my parabola, I see that looks like a tangent up there, so I might as well hit it. And here we get several things. We get the point of tangency B, we get the tangent, and we also get this parameter T, which is defining where B is along that curve. Now, while we think about T, I'm going to change the color of my curve. Make that blue so it doesn't interfere with other curves that I generate. So what is this T? Well, it depends on what kind of curve you have. If you have a parametric curve, it's the parameter. If you have a function, it's the x coordinate. Now we can open up this panel over here, which is our numeric panel, and we can see, in fact, there's t, and there it has a value, and as we drag t, the value changes. As we drag b, the value changes. And we can verify, we can add an expression up here. Look at the coordinates of b, and we can see, yeah, the x coordinate is in fact the same as t. Down here, we have the symbolic panel. So if in this symbolic panel, if we ask for the coordinates of b, we get t squared. So numeric panel over here, symbolic panel down here. What I want to do is create a line parallel to the x-axis. Now, when I'm using my constraints, I like to, when I sketch, make it obvious to myself that I haven't added the constraint yet. So rather than drawing it horizontally, what I like to do is draw it a bit off, so that if so that I remind myself, yes, you need to make that square. So let's do that. Make it square to the axis. And then what we're going to do is we're going to reflect that line in the tangent. Let's use my reflection construction, which is this one. Reflect that in the tangent, and we get the line there. So what we want is the envelope of that curve, the curve which is the envelope of that family of lines parameterized by t. And this is the thing that does that. We get to choose what the parameter is. Well, we only have one parameter in our drawing, so there's no choice there. There's our parameter t, there's our curve. Now we have part of the curve. It kind of stops there and there. What it's done is it's given us the limits on t that were up here. And you see t is going from 0 to 1. I'd rather see both sides of the curve, both halves of it. So let's go from -1 to 1. And we'll have our curve looking like that. So this is the caustic curve. We can see as we drag this round, we can see that it is in fact tangential to the entire family of lines. So what's its equation? We're told in my book that it's the Chernhausen cubic. So let's just take a look at what the Chernhausen cubic is. Go into our symbolic panel here, and as for the equation of the curve, we can't see the name, but we can grab the name just by selecting it. So called K naught. And there's its equation. Well, it is a cubic, barely. It's got one y cubed in it. What else can we say by looking at that equation? Well, clearly it doesn't have a constant term, so clearly it goes through the origin, which we can see there. What I would like to do is work out where this crossover point is. It's on the y-axis. X equals 0, we're going to get a cubic in y which has a factor y, so it's really just a quadratic. I'm guessing you could solve that faster than me, because I'm going to do it using WolframAlpha to show you how to use the algebra system hand in glove with the geometry system. Now, if I want to copy this expression into WolframAlpha. Notice I'm talking about equation. The equals 0 has been missed off. There's an implicit equals 0 here. But I would like to copy that expression into WolframAlpha. Now, if I press copy, I get it in a form that's useful for pasting into GXWeb, but not very useful for pasting into WolframAlpha. The way to get a copy that I can paste into WolframAlpha is to copy the text, and so that's what I'll do. Notice when you hover over this, you get copy, but when you hover over copy, you get copy text. So let's go into WolframAlpha. And paste that thing in there. So the nice thing about WolframAlpha is that when you give it something, it sort of bombards you with information about the thing that you gave it. So you frequently don't need to actually ask it for anything specific. So here's a picture of the expression we have, and we see, yeah, that does indeed look like what we were looking at. So nothing surprising there. Some alternate forms, but look, we've got real roots, and one of the real roots has got x equals 0. That looks exactly like what I want. Y equals 9/4. So let's come back into GXWeb. I'd like to create that point just to verify that I've got the right point. Now, I want to create a point at the location 9/4. There's a bit of a problem if you let the point snap to something, because you've then partially constrained it, and the system won't let you override that partial constraint with coordinates. So what you have to do is stick the point into a vacuum there, and that allows you, when it's selected, it allows you to specify its location, 0, 9/4. And sure enough, that shows up on our cubic. So so far so good. So we know that we have the Chernhausen cubic, which is formed as the caustic of light that's coming in horizontally. What if the light comes in vertically? Well, if the light comes in vertically, parallel rays of light, this is the thing that we really know about the parabola. It's all going to reflect into the focus. And so the caustic curve for light coming in parallel to the y-axis is degenerate. It's just a single point. It's that single point A. So we now have actually two caustic curves here. We've got the Chernhausen cubic for horizontal rays, and we've got the focus for vertical rays. What if we have something that is neither vertical nor horizontal? Well, let's try that. The book doesn't tell me, so I'm now off the book. Let's bring in some incident rays at some other angle, and not vertical, not horizontal. Let's go halfway between. So we'll make it pi/4. And we're going to do the same thing to get our curve. We're going to have to take that and reflect it in the tangent, and take the envelope of that reflected family of lines as t varies. This is where I got a surprise. That was not what I was expecting. I did not expect to see anything that looked at all similar to light coming in horizontally, because it seems to me that a parabola doesn't have that kind of symmetry. This looks like it's a twisted, shrunk version of that. Maybe it is, maybe it's not, but we'll have a look. So there's my curve for pi/4. What is this equation? Somewhat more complicated. Still a cubic, obviously. What, I wonder, does Wolfram make of this? So let's copy that as a piece of text, and we'll stick it into WolframAlpha. I have to apologize for all these kind of ugly parentheses that show up from GXWeb. Always worth making sure your input looks kind of like you expect it to. With WolframAlpha, sometimes doesn't quite something goes wrong in the process of interpreting the input. But this picture shows that yes, it does look like what we're after. Various different pieces of information, but we've now got, it's giving us a bunch of discrete points on the curve. Of course, there's an infinite number of points on the curve, so there's a lot of them. There's nothing to indicate which would be the one we would like, but my inclination is always to start off with the easiest looking one, which is that. And so let me start off by just taking a look and see where that point lies on my GXWeb model. So again, I don't want it to snap to anything. There's a lot of stuff to snap to, but we'll stick it way off there in space, and then constrain its location -1, 5/4. And yes, it was a lucky guess. I have to say, I did pick that the first time I went through this. It's not just prior knowledge. But I start wondering at this point, okay, I wonder what, I'd really like to do a general version of this with a theta rather than a pi/4, but I'd also like to generally stick a point on that intersection, if that intersection exists in a more general curve. And so my question then becomes, well, which value of t is going to contribute that point to the caustic? Somewhere around about where I am just now. I don't know what value that is at the moment. I'm at 0.872. What I'd like to do is solve for t, solve something for t, but because these equations are implicit equations, the t has been eliminated from them, the equation in terms of x and y. However, we do have the ability to get the parametric equations. So let's get the parametric equation of this curve. Now we have x and y as function of t. And so what I'd like to do is find the t which puts that x at -1. And that would be the value of t, which contributes point D to my curve. Well, let's go and ask WolframAlpha. We'll copy text. It's all or nothing with the copy. I get it all or part of it, or yeah, I get it all at once. So I don't get to choose which bit I copied there. So there's my expression. It's an x and a y, and that's not what I want. What I want to ask WolframAlpha is, I don't want the y there. I want to say, how about that equal to -1? How about that equals -1? What do you say to that? Well, it's interpreted the input. Looks like it's correct to me. It's plotting it. It's got alternate forms, and there we have what we wanted with solutions. 3 solutions. Seems reasonable. It's a cubic. But I like these two the best. They're plus and a minus, and they're symmetrical. They smack of the right solution. I'm just going to actually be altering t in my numeric panel. So let's just look at them numerically. 0.866. And so let's go up to my panel. But it was the square root of 3/2. We know that. What has happened to my? I've now gone totally confused here. Sorry, I pressed the wrong button. I wanted to go back there. And where was I? I wanted to put 0.866 up here. Well, that looks convincing on a visually that this line is contributing that point. Let's look at how about this point? What value t contributes that? Well, we can look for the parametric equations of this curve. K0. Well, that looks easier. The x coordinate in this case we want to be 0, And so we're solving the equation 3t over 2 minus 2t cubed equals 0, or t squared equals 3/4, or t equals √3 upon 2. So we have two data points which say that the location t equals √3 upon 2 contributes this double point to my caustic. Well, at this point, we'd like to have a look at a more general curve. More general situation where instead of pi by 4, let's make that phi. So now we're able to change phi and move this around and watch what it does in general. And in general, it does indeed seem to preserve this curious spiral symmetry. Let me just make phi go between sensible values. 0.75 minus 1.75. And we can take a look at how that varies. So we're getting a shrinking all the way down to that focus once we get vertical, and then we're coming out like this back up to this Schönhausen cubic at this point. So let me do a couple of things. Again, keeping my drawing clean as I go. Let's hide that thing. What I would like to do is stick a point at the, kind of move this around a bit. I'd like to stick a point at this corner where the line crosses over. I can put a point in general on my curve, and it will give it a parametric location S. So that's a parametric location on the curve, and as we move it backwards and forward, it will, now I haven't got it. Grab it. We can move it backwards and forwards. But what does that actually mean? Well, I can find that out if I just change it to T. So now I see that if I'm at the parametric location T, what that means is that I'm being contributed by the line, the tangent that is contributing to the caustic, to the envelope, is the one that started at point T on my original curve. And so therefore, if I change the T to √3 upon 2, that would be the point generated by T equals √3 upon 2. And lo and behold, let's hide that off again. Lo and behold, that sits at my double point, and I can watch that go around. So I'm going to do a couple of things here. First, I'm going to hide these off. Constant war to keep my diagram clean. I want to do two things. One, I want to have a look at what the locus of E is as phi varies. I can do that using, instead of using it as an envelope, I'm using it as a locus. I get to choose T or phi, and it's phi I want. And that looks very much like a circle. It is, in fact, I'm not going to bother looking at it, but is a circle that goes through, as we can see, A, the focus, and this point C, which is 9/4, so center by 5/4. In a minute, I'm going to ask the question. So think of it, that is the locus of the point contributed to the caustic by the point where T is √3 upon 2. I'm going to ask in a minute, is that a general thing or is that very specific to this diagram? That there should be a circle, which is the locus of the point contributed to the caustic by a specific point on the mirror for different angles of incoming parallel light. But that's a question for a moment from now. We'll hide this right now. What I'd like to ask myself is it really true that this thing's just a similar to this? And can I work out what transformation would take this grey one onto this red one? Well, first of all, I'll change its color so that we're going on to the yellow one. Well, if there is, I'm postulating that it's going to be a rotation followed by a scaling, and I believe that this is the fixed point for both of them, just by eyeballing what is going on when this thing's moving around. So that's what I'd like to do. Unfortunately, I seem to remove my point E when I remove my when I hid this. So let's get it back. All right, that's rehidden. And let's change that color again back to yellow. So first step is a rotation and then a scaling, I believe. If I can get the whole curve, one curve onto the other, then certainly the crossover point is going to have to, C is going to have to map onto E. So what is the transformation that takes C onto E? First of all, we'd like to know what angle is in between them. Angle CAE. That's phi. Okay, so let's do that. We want to do a rotation. It's a rotation transform there about point A, and the angle we're going to rotate is phi. That puts a new curve there. Hide this thing away. We now would like to see what the scale factor is, so we need to know distance from A to E divided by the distance from A to C. Cos phi. So we now need to do a scaling on this one. So we dilate with a center of dilation A and a scale factor of cos phi. And it lands right on top. Of course, I'm appealing to your visual sense. We could do exactly the same thing looking at the equations, and it would in fact work out. So at this point, I have we've seen that this Chernhausen cubic actually gives us the curve for any incoming angle. I would like to, at this point, take a little sidestep and answer the question that I put on hold as I was going through the question of how general is this idea that the point contributed to the caustic due to a specific point on the mirror, the locus of that is a circle. And let me examine that in generality. We'll need a new model for that. So there we go. We don't need axes though. So what I'm going to do, here's a general curve. Well, actually, it's 2 points extracted from a general curve, A and C, and the intersection of the tangents to their curve. I'm going to specify the angle between the tangents to be theta, and I'm going to bring in a couple of parallel rays. There's one ray. There's another ray deliberately made not parallel in order that I know that I need to constrain them. So we use the parallel constraint up here. And so we now have two rays coming in parallel, hitting a mirror that's not there, but whose tangents are here. And I would like, just so I can modify the diagram, I'd like to specify the angle that these guys are coming in, phi. And so that means I can come up here and tinker around with that, with this angle. Okay, so this ray reflects in this tangent to our invisible mirror, whereas this ray reflects in this tangent. Now I would like to alter my phi a touch just so I get a somewhat cleaner location for the intersection. And let me create the intersection there. So that is the point that I'm looking for the locus of this intersection as phi varies. Well, if I'm looking at it carefully, I can actually notice that this angle doesn't look like it's changing. And so rather than look for the locus, what I'd like to do first is actually just look for the angle. So I'm asking for the angle ADC. And we see 2 pi minus theta. Now, sometimes what's most important about a symbolic result is not what's there, but what's not there. And what's not there is phi. So that does tell us that this angle stays constant, regardless of the input angle, which then tells us that D must lie on a circle through who's with the chord AC. So let me construct that circle. And we can watch, we can alter phi and watch D, in fact, go around the circle. So this is think of it, this is the locus of the intersections of lines reflecting in two finite points, finitely distanced points on our mirror. Is there a way we can kind of figure out what that circle is without actually reflecting the lines? Well, the most obvious circle to actually put in place with 3 points is the Circum Circle. So let's just have a look at that. And the nice thing here is that it definitely looks like the center of that Circum Circle is lying on our locus. Well, we can check that that's actually true this way. Let's just ask for that angle AFC. See, yes, in fact, 2 pi minus theta, so that is the correct place. So if we want to get this circle, what we need to do is take 2 points on our curve, find the intersection of the tangents to our curve, find the circumcircle those, and then find the circumcircle of the 2 points and the center of that circle. So let me just take a look at that with our y equals x squared function. Mirror of that form. So in this case, let me draw something that looks like what I want. It's going to guess it's a quadratic. I'm going to put in my x squared, and we will zoom in on that a bit. So, yeah, thank you. So I'm going to take 2 points on that curve. Notice it's given them parametric equations S and T. I'm going to change the T to be T plus S to be T plus H. And create, as we said before, create the tangents there. The tangents of the 2 spots. and then find the intersection of those two tangents. So now the little recipe is we find the circumcircle of these 3 points, and then we find the circumcircle of these 2 points and the center of that circle. And this, let me just change some colors so that I can talk about the purple circle. So this purple circle then is the locus of the intersections of parallel rays of lights which strike A and B and then reflect. So it's the intersection of the reflections, their locus. Now, of course, I can take H and reduce it. And so as it reduces, the purple curve is going to tend to a limit, which is going to be the locus of the points on the caustic curve, the limiting curve. Well, I'd like to draw that limiting curve. Thinking about it, a couple of things occur. First of all, it definitely has to go through the point A. Secondly, it should be tangent. As we can see, the tangents are all gathering up. It should be tangent to the tangent of A. So let me just draw a circle that does that. It goes to A. It's tangent to the tangent of A. So all we need now is a radius, and we're done. To get the radius, we're going to ask help from WolframAlpha. So let's find the radius of our purple circle. That's our finite one. Looks like that. We want the limit of that as h tends to 0. The nice thing with WolframAlpha is you don't really need to remember what the command is for something. Just type it in, limit of, as h, I don't know, approaches 0. And it'll think about it a bit, but it's interpreted it correctly and it's giving me an answer. I want to copy that answer back into GXWeb, but I don't want all this stuff. So if I click this, I get the answer on its own. There it is, the input. I can't copy that, but I can get copyable plain text from Wolfram. So I click on that. I've now got copyable plain text and Wolfram language code. Well, that's not going to help me. This one is. So we copied the copyable plain text and go back into GXWeb. That's the radius I want to use for this, my limit function. Just paste that in. And there's my limit function. I can verify that as we go, as we approach the limit. That's where it is. And so we could see the limit function as t changes to different locations. And of course, there's one very special position for that limit function where it is symmetric, where f hits the y-axis. And we can find that, of course, by asking what are the coordinates of f. 3/4 t over 4 minus t cubed, of course, that's the square root of 3 upon 2 location. So let me just finish up with my going back to my slideshow here. Anyone that wants to follow me down a giant rabbit hole where we start talking about the Chernhausen cubic as viewed as a Bezier. It turns out it's a cubic Bezier spline with a control polygon, which is an equilateral triangle, and one can work through reducing this whole problem to one of triangle geometry. That's all sitting there on a sequence of YouTubes which will take you about the same length as this talk to go through at geometryexpressions.com/ATCM 2020. And there's my email, and I want to thank you very much for your attention.
Thank you very much, Bill. Any questions, comments? JJ, you had a question on your chat.
Yes, during the presentation, at the moment, you have displayed an angle for ADC, and JX displayed 2 pi minus theta. I thought it was pi minus theta. If I made a mistake, explain, please.
So I didn't quite. What was pi minus? With GXWeb, it's sometimes a bit unpredictable about which angle it's going to put.
Was ADC at the moment? You displayed ADC, and ADC was displayed as 2 pi minus theta.
Right. So, where were we? I'm not quite sure. Probably I've eliminated that, haven't I?
No, earlier.
That was the triangle on its own that you were talking about. You were looking at this model here.
I think it's the second example, Phil. Yeah.
Yes, you have this angle was theta, and this angle was pi minus theta. You know, because these 4 points were on the same circle.
I'm not quite sure the question is though. So this was the model.
Yes, you have theta here.
One of the nice things about GXWeb is you can't save anything, so you're always starting from fresh.
If you draw the circle passing through ABC.
Right. So you're getting phi there, and then we reflected this and this, and we reflected this and this.
Yes.
And then we asked for the angle.
Yes.
That angle there.
Yes. ADC.
Yeah, 2 pi minus theta. Right, but it's constant with respect to phi. So theta, in a sense, is a parameter of this whole thing. If you change theta, if you change the size of theta, it's going to be a different circle, obviously. But the point of it was it doesn't involve phi, so it's hence the locus as a circle. I guess you could have just done a locus command here, of course, as phi varies, and got the circle that way.
Yes, I understand. Okay, thank you very much. It was a misunderstanding. Thank you. Thank you very much.
Phil, this is Doug Mead.
Hi, Doug.
How are you?
Good.
It's always fun to watch this stuff in the hands of a master. But the question I have, most of us watching this learned our geometry the old-fashioned way, and so we have our intuitions, and we have our point of view on this. But how does this work for someone who doesn't know any geometry yet, and how does that change the way they learn geometry? Does that make sense?
That's interesting. You see, I'm an example of such a person. I didn't learn geometry the old-fashioned way. I hardly learned geometry at all. So most of the geometry I know I've acquired by using geometry expressions over the years. I'm a wee bit facetious there, but the discovery is the answer. You know, discovering the sort of things that but you know, sort of exploration and discovery.
And I think in discovery beyond just the geometry, the fact that you can discover something that you didn't know, that you can go out and figure something out. You can get some evidence. You can deduce some things. You can check things in different resources. I mean, I think that's, you know, I think that's, I mean, to me, that's one of the problems with mathematics education is that it's so rigid and so, well, I'll say formulaic that you're just, I mean, and I mean, what you said is true too. I mean, yeah, I had the geometry the old fashioned way, but how much of it do I really know? How much of it do I really remember? That, you know, if I can't put it back in that context, do I really?
Yeah, I'm guessing the place where I am using the geometry in the old fashioned way is that as soon as I saw, now of course this is a well-known thing, the geometric optics, but I don't know any geometric optics particularly, but as soon as I saw that angle as being constant, of course, because I did learn geometry the old fashioned way, I thought, oh, okay, constant angle means that the circle. Whereas when I was, it was an intern, we've had several interns playing with problems of this nature. And you know, these are high school students, and it was interesting because the particular one that worked through this little bit, the constant angle didn't mean anything to him. You know, I mean, he was a very bright student, a very, very well, you know, he did calculus and all that kind of stuff in junior year, etc., etc. But you know, constant angle inside in this kind of configuration didn't shout out it's a circle to him.
But you know, but I think, I mean, what you said there about the optics. Well, I mean, right now, in most contexts, that's just not tractable to but with the tools that you've introduced here, it is tractable. It is accessible to novice students who haven't seen this kind of stuff. So you can make those connections to physics, to other settings where it's not just, you know, not just a set of axioms and theorems and corollaries that, but we still have a long way to go to get the world to see things that way.
Yeah, I was the WolframAlpha. It's interesting the way you just don't have to know the syntax and how much that frees you from the fact you can ask for a limit and not have to remember the syntax for asking for a limit is a real, you know, really frees you. In the same fashion as you can ask, you know, you can ask Google various different things in just ordinary English and it will respond and understand. So that I felt was really quite a strong thing. The fact that you're going into an algebra system and not even asking for please solve this, you just give it and it gives you as much information as it can throw at you about the thing.
Well, you know, I mean, I wonder how other people might respond to that, because, you know, sometimes WolframAlpha gives you lots of things that you didn't even think to ask for, and you have to then still figure out what it is, you know, pull out what you need from what it's told you. And, you know, a lot of people just want an answer, and you still have to think.
Oh yeah, no, I'm not saying you don't have to think. WolframAlpha definitely has its negative side, because if you don't quite get it right, what you're asking for, you can get all kinds of rubbish back. But you just have to make sure it is interpreted what you're asking for correctly before you start believing what it gave you back.
Okay,
anyway,
I'm sorry to interrupt. If you have any more questions, feel free to communicate with Phil. And just remind everybody the next session starts in 4 minutes in a different room, and just send out the meeting ID and passcode to everybody. Let's thank Phil again. Thank you very much, Phil. Thank you, Phil.
Absolutely sure.